Hey there and welcome to this video. In this video I'll be talking about flow matching. If you haven't heard of this technique, it's the method behind Stable Diffusion 3, Flux, and also the very recent text-to-video model by Meta called MovieGen. Now, before you get angry that you have to learn yet another method for generative modeling after you potentially already put a lot of effort into understanding diffusion models, let me tell you that flow matching is basically just like normal diffusion models, but with some simplifying changes. In my opinion, some of the questionable choices in papers like DDPM or EDM are changed into much simpler versions in flow matching. And by the aforementioned models, you can definitely believe that this works and also scales. Now, how will this video be structured? At first, we'll do a quick introduction and explain the problem definition that we're trying to solve. Second, I'll give you an intuitive derivation of flow matching, which is extremely simple to understand and might already be all that you need for this entire method. Third, we'll place flow matching into the bigger picture of diffusion models, such that you understand the core differences between this approach and the more typical ones that you might be used to. And then fourth, we'll do the full derivation as they also do it in the paper. And then last but not least, we'll do a code example where we implement the approach in PyTorch. Let's briefly recap what the goal is that all of these different methods have in common. They all try to generate data and assume we have a bunch of data samples that we can learn from. For example, if we have a bunch of images of trains, the goal would be to generate new images of trains that are not in our existing data, but still could likely be in it. Now, we approach this as the following. We assume there is some underlying data distribution that these images come from. We can call this data distribution P1 of x1. We don't know P1 of x1 and can sample from it, and therefore want to learn a neural network that can help us to approximate and sample from it. Moreover, all the diffusion methods, flow matching included, take the approach to generate new data by starting at some known distribution P0 of x0 that we can sample from, like a standard Gaussian distribution, and then use the neural network that we learn to slowly turn this into something that could come from the actual data distribution P1 of x1. Now, after diving into this topic a lot and spending hours reading and understanding the specifics of the paper, I realized that the whole idea of flow matching basically boils down to just two formulas. Which is kind of sad because I'm literally here making a whole video about the paper, but super cool at the same time because the idea is just so simple. Now get this. You want to go from your noise distribution, for example a Gaussian distribution, to your data distribution, following some path between the two distributions, and you want to learn a neural network that can learn this path or trajectory. Say x0 is your noise and x1 is your data. Then the simplest way to construct such a path between noise and data is by doing a linear interpolation. That is literally the easiest possible way to do that. In the formula, you have t going from 0 to 1, such that when t is equals to 0, we're at noise, and when t is equals to 1, we're at data. But we can also be anywhere in between. Now, if you visualize this for a dataset where this 2D checkerboard is our data x1 and this is our noise x0 from a standard Gaussian, then if you start at t equals 0 and you slowly go to t equals 1, then this interpolation looks like this. And now here comes the big thing. This here is a function, right? And what we're interested in learning is the change of this function as this moves in time from noise to data, from x0 to x1. Specifically, we're interested in the derivative of this function with respect to time, because this would tell us that for a small nudge in time, for example from 0.1 to 0.2, how xt changes. And this change literally defines the process of moving closer to data, and that is all that we want, right? We want to move from a random x0 to a new data point x1. And now look at this. If you take the time derivative of this, you end up with this. Boom. That means we can try to train a neural network that learns this quantity here. Specifically, the model would take xt and predict x1 minus x0. And this is a vector that points towards x1 from x0. So exactly where we should go to get closer to data. And here comes the wild thing. This is exactly the same conclusion that the flow matching paper has after going through many math steps. And like, how cool is that? These two formulas don't just give you the solution of a big paper, but you literally have a whole intuitive derivation of the idea of flow matching, which powers all the big generative models by top companies nowadays. Now, in the rest of this video, I will still go through the derivation that the paper is doing in case you're interested in that, which also goes more into the details and covers why certain assumptions work out. But if you already understood this simple derivation here, that is basically all that you need. And also remember that after the derivation, we will do a code example with the data that we have here, which also applies to other data like images or videos. When I first started looking at the flow matching paper, I was so confused because the derivation is motivated so differently than the typical diffusion model papers. Instead of just starting with their approach, I first want to show you how they all fit into the bigger picture, something which is not mentioned in the papers. So basically, all papers try to learn P1 of x1, which includes learning all the different pt of xt, in order to move from P0 of x0, the unknown distribution, to P1 of x1, the known distribution. Now, as far as for the videos that I made about score matching, DDPM and now flow matching, there are three different ways to approach learning pt of xt. Score matching is taking the score of pt of xt by applying the logarithm and then the gradient with respect to x. DDPM is starting from the negative log of pt of xt, and flow matching says that pt of xt is generated by something called the flow, whose notation is psi t of x. So basically the same way we theoretically get xt from pt of xt, we can use psi t of x to get xt. Now, this doesn't explain anything so far, but now psi t stands in an interesting relation, which is the following. We have another function in here called ut of x, which makes things even more confusing. And what even is this time derivative? Well, for a second, let's replace psi t of x with xt, and now the formula looks like this. And now this seems a little bit more digestible. This means that the way xt changes, or flows, is determined by ut, which is a vector field. And if time flows from 0 to 1, from noise to data, then ut points into the direction that you have to move xt to get closer to data. This is really crucial to understand. If you are at xt and you move a little bit further in time, this gets you closer to a data point, and this direction is defined by ut of xt. And theoretically, if we know ut, then we could plug in any point and ut could tell us in which direction we have to move to get to data. But well, we don't know ut, and that is why flow matching tries to approximate this vector field by a neural network vt, such that the outputs of both functions become approximately the same given xt. And we will get xt from a flow psi t, or what you could also call the noising function. But we don't really have a definition for this either. But we'll get there. And first, let's define the objective that we're trying to minimize. We will try to learn a neural network, vt, which tries to approximate ut. As we have just said, we don't have access to pt of xt, and we also don't have access to psi t of x, and therefore also not to ut of xt. But to be able to train, we need a way to construct pt of xt, and also need a way to get the vectors from ut of xt. And the approach to achieve that is basically the same as what we ended up doing in the score matching video. To get there, let's start rewriting this objective until we have something that we can actually train with. First of all, we applied the algebraic identity, what you might have learned in school already, and now we will focus on this middle term here. We can rewrite an expectation to an integral with this reformulation. Now the next step might come a bit out of nowhere, but I will explain this in a second. We will apply marginalization and will rewrite ut of xt as the following. And this now looks super complicated, right? But let's understand this step by step. First, keep in mind that this here literally represents the same thing as the left side, specifically a vector pointing towards the data manifold. Now this here is a simpler version of a vector field, which only depends on a single data point x1. Let's do an example to understand this. Say we have the following data set of points, a 2D checkerboard, where all of this belongs to the data space and these gaps don't. All of these points belong to P1 of x1, and we will use a standard normal distribution as P0 of x0. Now, so far we haven't defined how the intermediate pt of xt look like, such as p0.5 of x0.5. And for the sake of this example, I will show this to you here without mathematically defining anything. But as you know from the beginning of this video, this will simply be a linear interpolation. We will talk more about this later. Now let's look at this awesome transition how our data points are moved to our noise distribution. Awesome. So we said ut of xt points towards our data, right? Generally, this is hard to define, but this here seems to be much easier since this vector depends only on a single data point. Say we have this point xt, and if we choose a random point from our dataset, for example this here, then the vector towards our data point would be this. Easy, right? And now this formula simply gives us a nice connection between the general hard to approximate ut of xt and the simple ut of xt given x1. Specifically, this says that we integrate over all of our data space. Practically speaking, we would go over our entire dataset and calculate each vector and weight them by this term and then sum them up. So we have a weighted sum where this factor decides how much influence each data point / vector has. Now this factor depends on how likely a data point x1 is to be at the position xt at time t. This is basically expressed with this part here, because pt of xt given x1 is a probability density function, or PDF, and this returns a high value if x lies in a dense area, and specifically here this is dependent on x1. To make this a bit less confusing, imagine this is our xt, and we choose this as x1. If t equals 0.8, then our data point could move to places that are very close to xt, given different random noises. And therefore, if we're at xt, moving into this direction would be a plausible choice. Other than this x1 here, because if we go to t equals 0.8, then xt is very far away, and therefore moving into this direction doesn't seem like a good idea. And this is exactly what this quantity would give us, a density value if xt is likely to occur around x1 moved to a specific time step t. And this down here is simply for normalization purposes that we still integrate to 1. By the way, keep in mind the dependence on t, since this xt is unlikely to be close to x1 at time t equals 0.8, but is much more likely at t equals 0.2. And now after we have this equality, we can plug this into our formula that we were rewriting. And now you see that pt of xt cancels and we are left with this formula. And now we move this integral to the front by making use of the Fubini-Tonelli theorem. And now we rewrite this back as an expectation, which gives us this. And we can plug this term back as the second part of the entire equation. And now we will do the same thing that we already did in the score matching derivation. We add this term to our entire equation and immediately subtract this again. And as we've seen already there, this is actually very useful because now we see that this here is the expanded algebraic identity, which we can write like this. Now let's just separate all these terms into their own expectation, and we can see that if we want to minimize this objective, these two terms don't include the weights we are optimizing, which are only present in our neural network Vt of xt, and therefore we can view them as a constant and therefore remove them from the objective. Now look where we started and where we ended up. We don't have access to this vector field ut of xt, but managed to rewrite the objective to use a much simpler version of our vector field, which only depends on a single data point, but an expectation still gives the correct directions. Awesome! By the way, in the paper, this objective here is referred to as the flow matching objective, and this here is called the conditional flow matching objective. If you watched until here already, I can tell you that this was the hardest part and that the rest of the video will be much more chill. If we look at this, we still need to properly define ut of xt given x1 and pt of xt given x1. Now how do the authors get to this? Remember the formula for the flow psi-t of x, which basically describes the act of moving x towards data. First of all, we can plug in the conditional vector field. Now, while this is still a very general formulation, the authors now go about actually defining the flow, and they first make this definition. Furthermore, they say that x comes from a normal distribution, and therefore we can just denote this as our x0, since this is literally our noise distribution. They describe this as the canonical transformation for Gaussian distributions, where canonical means that they are using the simplest possible form of linearly interpolating between two distributions P1 and P0 that involves shifting and scaling. On the other hand, previous methods like DDPM use a nonlinear interpolation, which adds a lot of complexity. And in flow matching, the authors really tried to go for the simplest possible approach. Now they define sigma t and mu t to be the following. And then the flow looks like this. And this is precisely the linear interpolation between noise and data we have talked about, just derived from the mathematical framework of the flow. Now let's take another look at our objective for the conditional flow matching. Remember this equation here, where we can also plug in x0 and get the following. Now, since this here is xt, these two are the same and we can replace this with the derivative of the flow. This means that what the neural network Vt needs to predict is the derivative of the flow with respect to time. Let's plug this in. And we can also rewrite the whole objective to only depend on x0 and x1 by also reparametrizing the input to the neural network. Perfect! Now let's find out what our neural network actually needs to predict and differentiate this with respect to t. And this is actually super easy since this is such a simple formula. And there you go. This is how we get to our objective and what the neural network needs to predict. And this is exactly what we got previously already when we looked at the super intuitive derivation at the beginning of the video. And now during training, we sample random noise x0 from the noise distribution and sample data points x1 from our dataset and sample t between 0 and 1, and then we calculate xt by linearly interpolating between x0 and x1 with the flow and give this as the input to the neural network, which tries to predict the vector from x0 to x1. And that's flow matching. A lot of maths and theoretical things to get to something so simple. And that is also why I really like the intuitive explanation from the beginning, which doesn't require this whole derivation but still logically makes sense. Anyways, this was the derivation as the authors show in the paper. Now, remember the 2D checkerboard example I showed earlier, which is also used in the paper. Well, since you guys always want some code, let's look at the PyTorch code to train a flow matching model to generate such data. And in practice, you can just apply this to any kind of data like images or even videos. First of all, in order to construct such a dataset, you can look at this code here. I'm not gonna go much into this since this doesn't have much to do with the actual deep learning part, and if you want, you can spend some time to go through the code yourself if you want to see how this is set up. All you need to know is that this code can give us sampled points, which if we plot looks like this here. So this is our x1, and for x0 we will use Gaussian noise later. For now, let's look at the neural network Vt that we can train. This here is a super simple MLP which has an in projection which projects our data that has 2 dimensions to a larger number, in our case 512. We also have a way to include the time step t by first applying cosine and sine embeddings and then a linear layer on top of that. Next, we add the time step embedding to the input and then apply a bunch of blocks which simply consist of linear layers and ReLU activations. Afterwards, we apply an out projection to project back to the input dimension of 2 and then we return x. And here we define the model and the optimizer, and now we can go to the training loop. We can train for 500k steps with a batch size of 64. Inside the training loop, we get a batch of x1 randomly drawn from a dataset, and here we define x0 to be Gaussian noise using the PyTorch randn function, and specifically ask for this to have the same shape as our data x1. Here we define the target, what the neural network should try to predict, and then we randomly sample time steps between 0 and 1 and interpolate x0 and x1 to get xt. And now we give xt and the time step t to the model and get the prediction and take the L2 loss between this and the target, and then we backpropagate the loss and take an optimizer step. And that is all that we need for the training. Now we can train the model and afterwards we can plot the loss, which actually in diffusion models never really shows that much, but now we can actually go to try to generate some new data points. The idea is very simple. We will just start with points sampled from the noise distribution P0 and then give this to our model to get the direction that each point should move to get closer to P1. And we will do this iteratively because otherwise there are much higher chances we drift off the actual path or overshoot the actual destination. Okay, here goes the code. First, we sample the points where we start from and we define how many iterations or steps we want to do. We will go with 1000 here. Then we will create a for loop for the 1000 iterations and always give the current positions to the model along with the time step, and then simply take the prediction of the model and add this to the current points multiplied by the step size, which depends on the number of iterations that we do. So let's say we have these 2 points and the model predicts these vectors. We take these vectors and multiply them by 1 divided by 1000 and add this to the points, which moves them closer to data. And that is literally all there is to generate new data points. How freaking cool is that the whole sampling code takes essentially just 2 lines? And while this might seem like a very simple example with this 2D dataset here, the logic doesn't change if you go to images or videos. That means in order to create these awesome images here, the sampling logic is literally this. Honestly, I'm so happy that such a complex seeming task like text to image or text to video can be approached with such a simple and intuitive method, which even achieves state-of-the-art results. That is how that should be. And if I have learned one thing over my few years in machine learning, then that simplicity will always win. And that is all for this video on flow matching. Before you leave, I have one quick announcement to make, which is that there's now a Patreon for this channel in case you really enjoy these videos and want to support me in making them. You can find a link in the description. Also, leave any feedback you have in the comments and some suggestions on topics that you would like to see. Because I think I now have covered most of the fundamentals of diffusion models, and especially with flow matching, there's so much less complexity to the whole field. Therefore, I'm very curious what other topics you would like to see. So yeah, share the video with your friends and I'll hopefully see you in the next one.